Okay, well, it's a pleasure to be here. Thanks for the great introduction. I thank the organizers very much for having me. It's been a wonderful meeting so far. And now comes my talk. So what I want to talk about is the things one finds in Fock-Goncharov coordinates. And I'll be touching on work with a bunch of people. So Alex Casella and Dominic Tate, with students at the University of Sydney with me. Robert Haraway was a postdoc there. Robert Löwe was a postdoc or a student. He joined me as a student from Berlin. And of course, my long-term collaborators, Daryl Cooper and Jean Porty, with whom I love talking about projective geometry. Okay, so without further ado, I just want to give sort of a brief overview of what is going to happen, with just sort of putting these four pictures into context. So I specifically put this image here because, so here, I mean, you have this kind of punctured surface, but the structures that you might get look like sort of surfaces with a totally geodesic boundary. Yeah? So what you see here is, in this triangle here, say, this triangle here maps to a triangle that sort of winds around then here, around the boundary component. I mean, I couldn't draw all of this. Yeah, and the same thing here. Yeah, so this kind of fills up this this pair of pans. As I thought, sort of pairs of pans were the running theme of the conference, so I should not deviate. Okay, so for Fock-Goncharov coordinates, I mean, we're going to start with something very, very simple, right? You have this triangulation, and if you wish, start with a closed-oriented surface of genus G. You have a triangulation with n vertices, and so these will be my punctures. So I'm really interested in studying the surface of genus G with n punctures. And so you have this ideal triangulation. And so you just decorate edges with 2 dots and triangles with 1 dot. Okay? So you have all these basically points on your surface. And now just associate positive reals, yeah, to these. Any positive real will do. Yeah? You're allowed to do what you want. Okay. And so this takes your triangulation now to a point in R to the 2e plus t. Yeah? So twice the number of edges and the triangles. And so you wonder, what can you do with this, right? And so I wanted to show you 2 different things you can do with this. And one is called A coordinates, and the other thing is called X coordinates. So let's start with A coordinates, because they're the easier thing. So here's my decorated triangle. That just has these numbers on it. Yeah? And now I want to sort of construct something that I call a concrete triangle. And so a concrete triangle is really going to be this. I mean, it's going to be a triangle in R3. Here's maybe one triangle. Let me put the origin somewhere. So here's the origin. And so what you want is, you really want some vectors here going out to these vertices. Okay, these are my vectors Ci here. So maybe here, this is C0. And I should always keep track of my orientations, C1, C2. Yeah, so these are my vectors. Fine. Yeah, and I want to choose these vectors such that the determinant, so stick the 3 vectors into just as the columns in a matrix. I want this determinant to be bigger than 0, and that's supposed to be my t here. Yeah, my t, my triangle variable. Okay, and so this is why the orientation matters, right? Because if I do it the other way around, I get the negative. Yeah, so this is why orientations are important. And now what I want to do is I want to choose hyperplanes. Okay, so hyperplanes through these kind of vectors here. So let me maybe draw one. So this here is supposed to be a hyperplane that contains this vector here. Yeah, okay. And what I'm now going to do is, I really want, I mean, now of course I can also think of this as a dual vector if I want to, right? And so the deal is now, if I evaluate this hyperplane, and this here is the kernel, say, of this R0, right? So here's the kernel of R0. It contains C0. And then if I evaluate it on C1, that's supposed to give me this number there that's called A01. And if I evaluate it on C2, it's supposed to give me the number A02. Okay? So that's all that we're doing. Yeah. So it's a very nice sort of simple setup that we have here. Okay. Yeah. People happy with this? Okay. And maybe one thing that's sort of useful here, I mean, I said before I want to look at projective structures. So here I'm in R3. This is my picture in R3. And of course, I can send this picture down to the projective plane. So this here is RP2, as you can all see. And so I get this kind of triangle in the real projective plane. Give the kind of projective classes of these guys. Yeah, so C0, C1, and C2. Okay, and then this hyperplane will give me a line. Yeah, so I get a line here somehow, like through this point. Yeah, a line through this point here. This is what I get. Okay, and now if I have all three of them, I get sort of something like that looks a bit like this here. I mean, I get sort of a triangle inscribed in another triangle. Okay. So this is where basically these positivity conditions come into. Yeah. So I have this kind of picture here. It looks very nice. Yeah. And now, of course, I said I have this for my whole triangulation. So there will be another vertex somewhere in my triangulation. Yeah. So imagine, I mean, here maybe we were looking at the one-puncture torus. So we had this kind of triangulation here, and we decorated the edges with these numbers. So I think that's all that I need to draw. Yeah, and so we've put down our first triangle according to whatever numbers I had. And then the deal is that this next triangle that I put in, say I want to put the next triangle here, the conditions actually ensure that the next vertex will lie inside this bigger triangle. And I again sort of get to draw sort of a hyperplane here. Yeah, and so it cuts out more and more from this kind of bigger triangle. Yeah, and so if I keep going, so my next triangle here, if I just keep doing this, I get numbers in the universal cover just equivariantly from whatever I had as a triangulation. So I keep building up this this kind of domain here, and like this here. And so you see very quickly in this picture you can't see anything anymore. Yeah, but this is kind of what the picture here was on this slide here. Yeah, so this is sort of the picture. What happens when you now start just developing this image here. Yeah. Mm-hmm. Yeah. Yep. Okay, so what you want is you have these numbers, and so what you want is that always R0 or Ri evaluated on Ci is 0, yeah, and Rj evaluated on Ci is bigger than 0, and this is supposed to be your coordinate Ji. Okay, yeah. And so what you see is actually, so if you sort of do a dimension count here, yeah, you will see that you really have 8 degrees of freedom. And so this picture here is actually, once you have these decorated triangle, so given a decorated triangle, there's what I call concrete triangle. I mean, this one here. And the concrete triangle comes with the vectors and the curve vectors. And it's unique up to the action of SL3R. Okay? So the deal is once I put down my first triangle, for the first triangle I have really the degrees of freedom up to SL3R, and then the whole rest of the picture is uniquely determined, yeah, by the decoration, yeah. So that is sort of the nice thing that happens here. And so I said uniquely determined. So here's our first triangle. We've put it in. And now maybe comes the next triangle. And it looks a bit like, I don't know, maybe like this here. Yeah? And then comes the next triangle. It looks a bit like maybe this here, and so forth. Yeah? And it's very hard to draw. I mean, I find it hard to draw these pictures in R3. I find it easier to actually look down here. Yeah? Okay. So what you see here is that, I mean, there's really two things that could happen, right? I mean, here, when you look at an edge, it might be that sort of two triangles that you see from the origin, yeah? They're sort of convex down, or if you look at it from the origin, it could be that, let me draw sort of the dots in about the same places. Or it could be that it sort of looks up, okay? And this really now, as you can imagine, you have this kind of structure on your surface, and this is really, it's a real projective structure on your surface. And so if it was a hyperbolic surface, you would say, well, you're really thinking about the canonical cell decomposition algorithm. Yeah? You really want to flip now to a canonical cell decomposition. And so you can do the same thing here. So if you think about this edge E here, right? I mean, what you really want to do is you want to flip from here to there. Yeah? So you want to, and here is this picture, maybe we're looking at it from above. And we really want to flip this edge here to this edge here. Yeah? So this is similar to what Loic was doing in his talk with the flip algorithm. Yeah? And so the nice thing is, so basically Cooper and Long tell you that there is sort of a canonical cell decomposition. Associated with this kind of, so what do we have here actually? So with the strictly convex real projective structure, given by this point P in T to the to E. Oh, sorry. Okay. And yeah. What is the property? And so the property, so in hyperbolic geometry, yeah, it is Delaunay, okay? But here basically we're not in this kind of fortunate situation that our domain is a nice round circle, yeah? Or that we sort of have this kind of Minkowski inner product, yeah? That's everywhere the same. And we're sort of looking at things that are kind of these, we're looking at these convex potatoes here basically, yeah? And it's actually, I mean, who would have thought that there is this infinite discrete group, yeah, just acting on this thing and giving you a surface as a quotient, right? I mean, it's kind of, probability should be zero, right? That there is such a thing. So it's actually quite nice that we here through this construction really get these triangulations. And so the condition really is that, I mean, if we look at this picture in R3, yeah, you really want to see a convex hypersurface. Yeah, that's what makes it canonical. Yeah. Okay, and this is exactly why here basically what I do is, so I have this picture, I have this PL surface in R3. Yeah, it's sort of wiggly, and so what I do is just I pick an edge and I flip it, yeah, in order to improve the surface. Yeah, and of course this is done equivariantly, and so this is how we keep flipping and so this kind of flip algorithm is actually determined by local information. So that's maybe the nice thing. I can do it intrinsically. I don't even need to draw anything in R3. All I need to know is a bunch of coordinates, and I always need to draw myself little thing in order to remember what I have to do. So the thing is, so there's this property of the edge that we call altitude. And so here the altitude of E is less than 0. And maybe this is E prime. And here the altitude of E prime is bigger than 0. Yeah? So this means we've found sort of an edge where we're sort of convex up. And you can actually write down the altitude as a function in basically these coordinates that I've drawn here. Yeah? So I don't know whether you want to see the formula. Maybe you do. You just want to see me struggle. So I take A times, so let's give these things names. E plus, E minus. Is this actually, can you see this in the last row somewhere? Kind of, okay. People have better eyes than I do. So I'll call this here maybe A plus. I'll call this here B minus. I call this here C minus, or call this here D plus. It doesn't really matter. And so now you can write this down. So it's A times the product of these two, E plus, A plus, plus, and then you have E minus, B minus, and then you subtract E minus, E plus. And then we do the symmetric thing here. So it's E plus D plus plus E minus C minus minus. Okay, so this is some nice function, right? It's of degree 3, but you can write it down. And so the deal is that because of the Cooper and Long result, what it basically tells you is, right, what could go wrong when you do this flipping? What could go wrong is that you just keep flipping forever, yeah? But keep flipping forever means that you have sort of a sequence of vectors that accumulate at 0, yeah? And so Cooper and Long in their proof basically show, no, this does not happen, yeah? So beneath any level, there's just finitely many vertices when you play this game here, yeah? And because there's just finitely many vertices, this algorithm sort of terminates. So a flip algorithm terminates. And you get this kind of structure, this kind of canonical cell decomposition, this canonical triangulation. Okay? So all I want to illustrate with this here is these A coordinates, yeah, are really nice if you just want to do some things intrinsically, like find canonical triangulation. Okay? But you also see that every time you do this, right? I mean, if you do such a flip, if you go from here to here, you see that some of these coordinates change, right? And you're changing sort of here these coordinates and these coordinates. Yeah, of course, this edge you didn't have before. Yeah, and these triangles change because all of a sudden, instead of say taking the determinant of these three vectors and the determinant of these three vectors, you're now taking the determinant of these three vectors and the determinant of these three vectors. Yeah, so the coordinates change, but there's a very controlled way in which they do. And you can also write this down intrinsically. Yeah? So you can write these down as rational functions on these coordinates. Okay. So I said a lot of things. That's a problem, right? And when you talk, it's very hard to write. So I did not write as much as I thought I might. What else did I want to say here? So, and someone asked before about sort of Delaunay and other things. I mean, so if you want to think about Penner's decorated Teichmüller space, okay, so this actually sits in there quite nicely. All you need to do is, so if you decorate a triangle, say you really want decorated or doubly decorated hyperbolic structures, yeah? So what you have to do is just on each edge, basically, don't use two different numbers, use the same number, okay? So really what we're doing is lambda coordinates, yeah? So Penner lambda coordinates. So here write the same number, here write the same number, here write the same number, and then the triangle So just give me this number here. Yeah. So just take the square root of 2 times ABC, and then you're good. Okay. So this is going to be, this then gives you hyperbolic structures. Okay. Doubly decorated hyperbolic structures. And if you do the dimension count, everything makes sense. Okay. So maybe one other thing that I want to mention before I move on to other coordinates. So with so what Penner does is Penner uses decorated structures in order to actually give you a canonical cell decomposition of Teichmüller space itself. Yeah. And so what we can do is we can do the same thing for these real projective structures. And I haven't actually set up any notation for this, right? So, so let's see. So here we sort of have maybe the Teichmüller space of hyperbolic structures. We've got it kind of doubly decorated, yeah? So my doubly decorated sign is this here on the surface SGN. And I think of this now as sitting inside these, let's just sort of use this notation here for these real projective structures. Yeah, so this is this kind of parameter space that I get here. And this here, once I pick a triangulation, is the same as r bigger than 0 2e plus t. Yeah? Okay. So I guess I've shown you one thing, right? I've shown you how once I pick a triangulation, how do I get sort of such a structure? Yeah, that's what I've kind of shown you. Yeah, through these pictures. But you can also go sort of the other way around. I mean, once you have such a structure, you can basically determine a point here. Okay, so this sort of goes backwards as well. Okay, and so with Robert Haraway, Robert Löwe, and Dominic Tate, we basically showed that associating with each point here, its canonical cell decomposition, that also gives you a natural mapping class invariant cell decomposition of that space. So obtain the natural by associating each point with its canonical cell decomposition. So there's sort of two different cell decompositions here, right? And there's a cell decomposition of the actual surface with a given structure, and then there's a cell decomposition of the whole moduli space, which is here. Okay. And the proof is kind of fun. I mean, so there's special points here. So if I think about these vectors in r to the 2e plus t, I can really think of this as r to the 2e plus r to the t. And so useful points to look at here is, well, make all the edge invariants equal to 1 and allow yourself for the triangle coordinates to basically be arbitrary positive numbers. And that gives you sort of a nice vibration of this space. And so that's roughly how the proof goes. I mean, you look at these slices where you basically pick the one vector and then basically you just let these coordinates here vary. So I guess I'm drawing it in that plane here. And so you get sort of these kind of slices for the cells, and I don't know what they look like. I mean, it's sort of this, maybe you get something like this here. So this is sort of the constant one vector, but then giving you different triangle coordinates. And here you can sort of show that this actually has sort of a fixed neighborhood, yeah? You can sort of determine a fixed neighborhood here. And then what you want to do is, in this proof that really these things are cells, what we do is we sort of show, yeah, that, I mean, here, these are star-shaped sets at each level. And then you basically want to show that you can really sort of make this, yeah, contract this basically to a cell, yeah? Okay. So I must say, for our paper, there's a paper on the archive which you shouldn't look at. So we got 2 referee reports, and one referee report said the paper is poorly written, but all the mathematics is correct. And the second one said, it's really beautifully written, but I think there's a small gap. And I agree with both referees, actually. So, I mean, the paper could have been written better, and there's a small gap. But, we fixed the gap. I mean, really it was sort of just a technical argument in this kind of star-shaped business, yeah? I had to use analysis, basically, to get over it. But anyway, I can deal. We had a discussion yesterday at dinner, and yeah, every now and then I can deal with analysis. Okay, so, but only if really needed. Okay, so this is maybe all that I want to say about, yeah?
Boundaries.
Oh, the boundaries of the, okay, so this is actually, Besson is, he sort of put his finger also on something. So this is really what the top dimensional cells look like. And then but you need to, I mean, in order to really show it's a cell decomposition, you need to show the intersections of cells are also cells, yeah? And so the lower dimensional, they look a little bit more awkward. So there basically the argument is actually sort of going from basically something that you have sort of on, basically there's sort of a stratification here where you sort of get level sets that look more like, yeah, cake slices. I mean, you can sort of cone to a point that's actually not in your cell anymore, yeah? And you can basically use this. Yeah, so so maybe if you're thinking about, I mean, what would you use here as your vector? So you really just do sort of the natural thing where, I mean, you have these cells where you want to put all ones here. I mean, I said use the all one vector. Let me keep indicating this here, right? Use the all one vector here. And then here, basically, the trick is actually to show it doesn't matter which triangulation you choose. And what you work with is you actually work with a triangulation where you cone everything from one vertex, yeah? And so that's actually a nice one to work with, yeah. Mm-hmm. Okay. Good. So maybe then that's all I want to say about x coordinates for the moment, about a coordinates for the moment. And let's see where we are here. Oh, and then there's x coordinates, okay? So x coordinate, that's why I left them for the second bit. X coordinates are a bit more tricky because really you want to work down here in this picture, right? You want to work down here in this picture, and really you want to work with the so the points in the projective plane and also the lines in the projective plane, okay? And so then, I mean, people who sort of think about projective geometry, of course, oh, I should take this down. No, there are nice things called triple ratios and also cross ratios that one can use to define quantities that are invariant under the action of PGL, yeah? And so here, I mean, here's sort of a triple ratio that we use, or that Fock-Goncharov use. So where you have these flags, I mean, again, you think of this as a flag consisting of a point and a line. Yeah, here's always a point and a line. So these are these kind of flags. And you can define a triple ratio of these three flags by just this kind of quantity, where the bar just means you take a representative, yeah, in R3, or in R3, the dual space, yeah? So this is kind of triple ratio. And that's what you associate with, say, the triangle coordinate here. And then for the edges, you sort of assign special triple ratios where you sort of take the vertices, but then also you take other edges. Yeah? So you take edges basically for, say, this one here, right? So the flag, the first flag that I choose, if I want to get the invariant of this point, is I choose this point in projector space and this line containing it. Then I choose VL is this point here, but you actually choose that line, okay? So that's what I mean here by VL, VK. I choose this line. And then as the last one, I choose VJ, and then this line here, yeah? Okay? And so this gives me then sort of the invariant associated with this edge, okay? So that's what they are. I'm sorry. And so again, you can show that basically once, so here now the deal is that once I give you a triangle coordinate, now I need to create some more space here. Yeah. So basically this triple, so if you give me a positive number, t bigger than 0, yeah? So what does this give you? It really describes an inscribed triangle, whoops, into circumscribed triangle. I always forget that it's actually easier to first draw the circumscribed triangle. Yeah? It describes this here basically uniquely up to projective transformations. Yeah, so this is sort of the nice thing that you get, and then basically you want to sort of carry on again. I mean, you can show here that if all these kind of coordinates are positive, yeah, you can sort of go between these inscribed triangles and circumscribed triangles and these coordinates, and so here now, I mean, you wonder how to put the next vertex, and that's again determined now by the edge coordinates, and then you also again get this new sort of hyperplane here by the triangle coordinate. Yeah, so this is sort of a similar process again, going from these x coordinates to a strictly convex projective structure. But there's now something else that happens here, and so in the previous case with the a coordinates, basically these were so what happens here is because you have these vectors in R3, right? These vectors are fixed. So actually your peripheral transformations are all parabolics, okay? But now basically, and so they fix these kind of fixed vectors on these rays. They don't just act on these rays. But now what happens here is that that's no longer the case. And so you get more general structures. And so the peripheral elements, I mean, the way they act is really determined by the Jordan normal form, if you wish. Yeah? So you have these kind of elements here, and you could have a peripheral element really go to what's called a totally hyperbolic element. So yeah, it's diagonalizable with 3 positive diagonal entries. And so if you think about the developing image sort of your surface, yeah, I mean, it lies somewhere here, but it might also include this here or parts of this here. Or, I mean, you're sort of in this mixed case, what's called quasi-hyperbolic. And so, yeah, right, I mean, here the peripheral element, I mean, it fixes 2 points and 2 lines, yeah? Or you're in this case here in the parabolic case, and that's sort of the finite volume case that we like, yeah? Okay, so maybe just to talk a little bit more about what's happening with these structures. So if you think about a hyperbolic surface with totally geodesic boundary, and you can also develop it into something like this here, right? So let me give this here a color. So in the hyperbolic plane, what do you see? right? In the hyperbolic plane, you see lines, and let me just draw all of this in the Klein model, because we're doing projective geometry here. Yeah, so you see all these kind of lines here, and maybe this here is a developing image of the, the cover of your surface, so here's my surface S. Yeah, okay? And fine, so you can either take the whole hyperbolic plane modulo the group, and you sort of get this kind of surface with a big flare, yeah? Or you could decide to just sort of act on this region here that's cut off by these lines, right? And so what you get is a structure on this thing here, yeah? But now the way I sort of talked about real projective structures is you're allowed to take any sort of open convex set, yeah? And so if you're allowed to take any open convex set, I mean, you could do crazy things, right? You could say, well, here actually I have the hyperbolic metric. Let's just take an epsilon neighborhood of this thing here, yeah? That's a perfectly fine domain that you could choose, right? Just sort of taking epsilon thickening of this here, and you can use that if you like, yeah? Or another thing you could do is just sort of pick a point somewhere here and act on it, and then make it sort of a piecewise linear thing, yeah? That would also be a perfectly fine domain to choose, yeah? So all of a sudden you have these kind of infinitely many domains that you could be looking at. Another thing that you could do, why not? I mean, think of the hyperbolic, I mean, here I'm already in the Klein model, right? Here you're maybe attracting and repelling fixed points, yeah? But you're really in this first case here, you're in the totally hyperbolic case. And so somewhere here, I mean, if you draw the two tangent lines here, right? And these are stabilized, and so you have this third fixed point here. Well, I mean, you could take as your domain, the domain where you add all of these kind of, triangles here on these things here, okay? So there would be another option for taking a domain, okay? So lots of possibilities, and you wonder what should I choose, yeah? And the thing is that these Fock-Goncharov coordinates, basically, they pick up all the possibilities for these kind of smallest domains that you can think about, and the largest domains that you can think about, okay? So in that sense, I mean, you see points, so let's go maybe to the picture. I mean, if you want to think about holonomies, so these kind of homomorphisms that I see here into SL3C that are holonomies for these structures. So look at these holonomies or structures, but really we decorate them, yeah? So that's what's happening here in this picture, in this Fock-Goncharov picture. You can decorate them by picking basically peripheral fixed point, and then you can pick one of the two invariant lines through it, yeah? So it's in this case, for this point, I could either choose this point in this line, or I could choose this point in this line here, yeah? So I have a choice for each cusp. So I can take these holonomies times, so let me just write like this, so RP2 times RP2 dual, and this to the number of cusps, yeah? So this is really these kind of decorated holonomies that I'm looking at, yeah? So let's give this a name, hol x of S, yeah? And then you have this kind of Fock-Goncharov space, this parameter space. So that's your r to the 2e plus t bigger than 0, yeah? And so this here, we really want to think of this as what? We want to think of this as giving us these kind of decorated structures, yeah? These strictly convex projective structures where we now pick sort of a point and invariant line on the boundary. Let me just, no. So there's two options that you basically have, okay? So there's two options for how you think about this parameter space. And so the one option is, I mean, I said you have these inscribed and circumscribed triangles. And one way to think about what you're doing is you could say, well, I'm thinking about building up my domain omega that I'm acting on from these triangles slowly, okay? So you have this increasing union of triangles that you're building up to be your domain omega. So let's maybe call this here omega plus. Another way to think about it is, well, you could say, let's take these circumscribed triangles and just keep intersecting them, okay? Yeah, so you take sort of a decreasing intersection of these kind of bigger triangles that you have there, yeah? So that's sort of, let's call this here omega minus, yeah? And so that gives you basically two different structures, as you see in these pictures here, yeah? And so there's one thing that you can build is kind of this T plus 3 of S, or you can build a T minus 3 of S. And maybe it's not surprising that sort of projective duality actually interchanges between the two of them. Yeah, okay, so there's projective duality here. And then from these here, you can go to these decorated holonomies. And again, projective duality basically interchanges between these two. Yeah, so you get this very natural way of looking at things. Okay, and if you want to sort of think about the geography of this space, lucky I haven't told you how many slides I have. So let's see. So if you want to look at the geography of this space, so here somehow, yeah, the whole big space of these kind of projective structures, yeah, projective structures and surfaces, strictly convex ones, which is kind of this infinite dimensional space because I allow myself to do whatever I want, yeah. Then inside this, I have this kind of space T plus 3 of S, and I have the space T minus 3 of S, and they have some kind of intersection, okay? And then here, inside here, are kind of the finite volume structures. They're sort of in the intersection because here for each, peripheral element, I just get one, whoops, over here, yeah, I just get one fixed point and one line. There's just no choice, yeah? Okay. So this is kind of how it looks like. And then when I think about these maps to this holonomy group, they just have sort of different degrees, yeah? So if I go from here, it's generically 6 to the cusps to 1, yeah? If I come from this kind of intersection here, then it's 4 to the number of cusps to 1, and so forth. I mean, there's sort of different strata that you can look at. Okay, and then what you see is, I mean, the representations, they have a really nice form. You can actually read them off from the information. So that's another thing that is nice for computational algorithms on these things. So if you have this kind of triangulation here and you have all your coordinates, yeah? So fix a base point somewhere. I don't know where, maybe here. And so then I've sort of drawn this kind of strange graph into my surface, yeah? And so now if I think about any element in fundamental group, I can think of this as I just keep going along sort of bunch of edges, yeah, in this kind of graph, okay? And then in order to get the related holonomy representations, all you just need to do is you need to write down these kind of matrices that are just given in terms of the coordinates, yeah? And you just sort of multiply them together as you sort of go along this graph, okay? So that's what these kind of positive representations of Fock-Goncharov are in this setting here, yeah? And yeah, so that's nice. And so that gives you a nice section, right, for the map where you really want to look at here not just conjugacy classes of representations, but you actually want to have sort of representations. Okay, so what do I have? I have 2 minutes. So let's see. So So one thing that I want to mention then is, and let me just say all these things. So, but write down some words. So there's a natural Poisson structure. And this Poisson structure, it actually, so I said you have a Poisson structure sort of here, yeah? But this actually is compatible. It agrees with the Goldman bracket. That's mentioned in one of the earlier talks, yeah? The Goldman bracket here. And so that makes this Poisson map. And this Poisson structure you can then use here to distinguish, for instance, between the moduli spaces of different surfaces, yeah? Because, of course, if the Euler characteristic of some surface is the same as the Euler characteristic of some other surface, yeah? Then these moduli spaces will have the same dimension. I mean, this here is just r to the minus 8 times the Euler characteristic of S bigger than 0, yeah? So the dimension somehow, these are balls of the same dimension, but the Poisson structures are only the same if the surface is actually the same, yeah? And otherwise not. So the Poisson structure sort of distinguishes these kind of moduli spaces. Another thing that I want to mention is, so there's a notion, I haven't talked about metric in area, right? So there's a natural metric called the Hilbert metric. So these structures that I'm looking at, I mean, generally they're only Riemannian if I have they're only Riemannian if I look at hyperbolic structures, and otherwise they're just Finsler metrics. But there is a natural metric called the Hilbert metric. Using this, you can get a notion of area. And then there's basically area bounds in terms of the coordinates. And so Adeboye Cooper gives sort of area bounds in terms of the triangle coordinates. Okay. But these are not sort of bounds on the nose. And so one question is, how do you improve this? Yeah, so question, how improve? So I'm in what Peter called the question section, but I'm asking the question. Yeah. So another question is maybe how can you get from these coordinates maybe the length spectrum? Yeah, especially seeing that we can actually sort of work out the matrix representation, say, of elements here of the holonomy representations. Okay, another question is sort of, how do you define metrics on these spaces, yeah? On T3 plus of S, or on this doubly decorated space. And there's a lot of metrics known for Teichmüller space, but yeah, how would you do this here, right? Because many things that work in Teichmüller space, they make use of the fact that we just have this, yeah? Lorentzian in our product, and we don't have this. Yeah, I mean, this is what creating often some of the difficulties also in proofs or trying to get analogous results to what they have. And then there's another thing, another question. Let me just put it here. Oh, -1 question. Okay, so I don't have time for that question. So then maybe one of the sort of most tantalizing questions is, of course, I said you have these kind of sequences of structures, and then what do they limit to, right? What do you get? And so one thing is, I mean, limiting things or maybe actions on A2 buildings. I mean, this work of Anne-Poirot also think of this as sort of a length function compactification, but you really wonder what kind of geometric structures you have. And so for some examples that we can sort of play with, you get sort of interesting structures that are kind of mixed structures sort of built on these buildings that are kind of like what are called hex structures. And the building sort of has a weird norm, a weird metric, and you get sort of interesting structures on corresponding to limits. But of course, one would make this into sort of a fully fledged theory, and maybe this is where I should stop. Here are the questions.
Yes. Question was about the area you can define. So for the hyperbolic representation, it's exactly the hyperbolic area, I guess.
I don't think so. No.
Oh, it varies.
Yeah.
Okay,
it varies. So the thing is that let me just write this down. The bound here is given something like the area of S is less or equal. I mean, you can take the supremum, of course, over all the infimum over all triangulations where you take something like I might get my constants wrong. So I'm going to G minus 1. Oh, let me just look this up. It's terrible when constants are wrong, right? And so what's even worse is, right, if you don't get the constants right, but the direction in which the inequality goes. So you take logarithms of the triangle coordinates, yeah, divided by 8, something like this, yeah? So this is what it looks like, and of course when you sort of flip, the triangle coordinates change, yeah? And so I don't even know whether you can sort of find one triangulation, yeah, where you get the right thing, yeah. Mm-hmm. Yeah.
And even if the surface S is the hyperbolic one?
Yeah, so I think even if the surface is hyperbolic, I think if I remember correctly, Dominic was able to get examples where even for a hyperbolic structure, this can be sort of arbitrarily bad, actually, this lower bound.
Okay.
Yeah. Oh no, sorry, sorry. Let's backtrack. For hyperbolic, right, everything is clear, right? Because for a hyperbolic surface, you just have ideal triangles, and so you know what, yeah? You of course know what the area is. Yeah.
Okay, is that the minimum area you can reach? So it always grows afterwards?
Whether the Finsler area is always more than a hyperbolic one.
And it's the hyperbolic one if and only if the area is minimum? Or?
I don't know, yeah.
Okay.
Mm-hmm.
More question?
You were talking about Penner's coordinates, which gives you a cell decomposition.
Yeah.
And those are polytopes, right, those cells? Is this for your decomposition as well, that your cells are polytopes?
Oh, no, I don't know whether they're polyhedral. Yeah.
Okay.
Yeah.
Just on that cell decomposition, do you know what like the things that represent vertices, like things that are in vertices or edges or smaller dimensional cells, like what they look like?
No, so one thing that we do know is, the cell decomposition, of course, it sort of interacts well with the cell decomposition of Teichmüller space. Yeah. So if you look at one of our cells, then sort of a Teichmüller cell, of course, fits in there, yeah, as sort of a lower dimensional cell. Okay. And so then one thing that we've looked at is, of course, you have sort of centers of cells, and Penner shows that of the top dimensional cells, what you get are arithmetic groups. Yeah. And then one thing that we could do with our coordinates is basically show that then the sort of the lower dimensional ones, the centers, are what are called semi-arithmetic groups. Yeah. So just from basically the nice sort of way of looking at these monodromy matrices. Yeah. But no, I don't know anything else about sort of how the cells sort of interact with each other, or what you can sort of find in the boundaries or the extremities. Yeah. Yeah. And often, what you get is, right, the cells are really bounded by these, altitude, yeah? Altitude conditions. And so really, they look like, right. and the way sort of the space is divided up is really, I mean, it looks like this here, right? And the dual to this is really then the, because mapping class group acts on it, yeah? You'll sort of find these kind of nice spines here inside there. Sorry? Yeah, and the thing is, you already have basically Teichmüller space sitting inside there, yeah. And the other thing that you have is, I mean, there's Benoit Hulin basically tells you that if you think about, Benoit Hulin tells you that if you think about sort of the projective structures, right, then you can really think of this as a Teichmüller space, yeah, on your surface, plus a vector space that's basically cubic holomorphic differential, yeah. So this already sort of gives you a nice sort of splitting here, and so really you can then use what you know about Teichmüller space, yeah. But one sort of other problem, I mean, that a problem that I sort of didn't mention before is, I mean, here of course the question is, right? I mean, if you give me now a point in Fock-Goncharov space, how do you determine, yeah, this sort of canonical hyperbolic structure that's associated to a projective structure? I have no idea. Mm-hmm. Yeah. Thank you.